The first talk is by Tobias. He's a final year PhD student in Professor Van Bever's group at ETH Zurich. His research focuses on improving the insights for ISP operators who can gain insights about packet paths in and outside of their networks. He's expected to graduate early next year and will be in the job market next year as well.
Thank you for the introduction, and let's directly dive in. So today, we only have a few gold nuggets of network data available. And I'm sure you recognize some of the names in this incomplete list on the slides. Yet in our research, we often need more data or data from different application types that is unfortunately not available. So we were looking for other sources. And we believe that we kind of found an entire gold mine or gold tile that is completely unused at the moment. At least we hope so. So what could that be? Namely, the ever-increasing amount of open source applications that we see on websites such as GitHub. GitHub alone currently claims to host around 338 million of repositories on the website. And this number is increasing every year. Just imagine the diverse types of traffic and applications found in all these open source projects. So what if we could dig in and take advantage of it? So in order to do that, we have to bridge a gap from like static text or code to the actual packets and traces that we see at the end. And there are multiple ways how we could do that. We could use techniques such as static code analysis to perhaps get a high-level idea of what a function produces. Or we could try to actually run the open source projects. That has the additional benefits that the traffic they generate is what we call live. They generate the packets at runtime, and they might react to network events, such as a packet loss, and then hopefully retransmit the packets. Or there might be a lot of other ideas that we do not even think about. In this work, though, we focus on the second aspect, and we try to run as many open source projects as possible in order to get diverse traffic traces from them. However, doing that at scale is quite challenging, as we need to run kind of arbitrary code written in arbitrary languages. Perhaps the documentation is missing, or we don't know what the run commands are. And even if the application is run, we might have not all the input parameters, or there might be other problems or crashes. So does that mean we cannot tap into this gold mine of network data? So actually, we believe there is still a chance. And that is the recent trend that more and more of these projects use kind of so-called automation frameworks that allow to build and compile the entire application with a single command, for example. And one of the most popular solutions are Docker containers, which contain all the code and dependencies in order to run one single application. Yet even more interesting are so-called orchestration files, which define how multiple containers interact with each other, are connected to each other, and a single command can then start all of them. So we were focusing on open source projects that have kind of such an orchestration file with the hope that we can execute all the containers and then hopefully get some network traffic out. So the higher level vision is that we can combine the so-called big data that we find on open source platforms such as GitHub with container solutions, for example, Docker, in order to present representative and live network traffic. So under representative, we understand that the traffic follows a given user specification and tries to be as close as possible. And live means that these applications really run at runtime, generate the traffic, and then react to events in the network. And in order to get to this vision, we present a system called Dynamo from Dynamic Mass Orchestration, which kind of works in 3 steps. First, we get some input from a user. You see a simple example there, which specifies the traffic we would like to get out at the end of the system. And then Dynamo first parses this input and then looks at an internal database which contains all the projects that Dynamo knows about that generate some sort of network traffic. And then tries to pick the best ones that match the given specification and reruns them with the hope that they now generate the traffic and we can use that either in a virtual or in a physical network. And one application of that could be, for example, that we can do that, use that for security testing, where Dynamo's traffic, which is might be quite diverse, used as background traffic, and then we have some attack flows on top, and we can see if a firewall still detects the attack flows. So in the next few slides, we will look a bit closer into all these different steps. So as I said, Dynamo needs to know which projects generate what kind of traffic. And for that, we can once again start with these 338 millions of repositories that currently are on GitHub. So we used various search API queries in order to identify around 2 million of these orchestration files that belong to various different open source projects. And then over the last 9 months, we had like 6 VMs constantly running, which iteratively tried one after each other in order to run them and then hopefully get some network traffic out. So a lot of them actually failed because of errors or because we did not have the correct run command or because of other problems. But we already identified around 74,000 orchestration files, which not only do they run, but they also generate some sort of meaningful network traffic. And for each of them, we currently recorded a trace in order to build this database that Dynamo can then later on use. So here, there is a lot of improvement potential because a lot of things that we did so far are kind of suboptimal. So I'm sure we can get this number much higher if we do different techniques in the future. Then a user has to specify what kind of traffic he or she would like to get out of Dynamo. And for that, we designed a so-called declarative specification language that answers kind of 3 questions. First, what kind of traffic do I would like to see? So in this example, web and database traffic. Between which hosts I would like to see this traffic. And these hosts are virtual hosts that Dynamo will create. And roughly how much of the traffic I would like to see. Dynamo then takes this input, this specification, and starts its internal process. So we want to get from this specification in the end to live traffic that more or less closely matches the specification. And as I said before, in the first step, Dynamo now queries this internal database with all traffic generating projects and kind of solves an optimization problem in order to find out what the best matching project would be to fulfill the specification. It then downloads and configures the corresponding containers that belong to these applications and reruns them. And in between, we add a so-called orchestration layer that can do some simple operations to merge flows together or to do some mapping in order to create this virtual hosts that are specified in the specification language. And then in the end, we get the live traffic out, and hopefully the user can then use it for its various applications. So for more detail on that, please have a look at the text. So we believe that at the moment, Dynamo's approach already allows us to solve various use cases. So for example, as I said before, I think Dynamo's traffic is quite diverse. There are a lot of different applications we could specify in the input, and therefore it might be a good idea to use this traffic in security testing. Because these open source projects could do anything. There might be attack traffic in it or whatever. So we can use that in order to see how a firewall, for example, behaves. And we could even add some attack flows on top of it that we know are malicious and then see if the firewalls detect. We could use Dynamo also for network design. Because we get live traffic, we can, for example, test how Bitcoin reacts to different packet losses. And we would specify some Bitcoin traffic and then send that through a network with various packet loss rates and then see how the application behaves. Or it might be interesting to actually take live traffic and then record traces out of it in order to enlarge or complement existing data sets, especially for applications such as ML, where often the data set might be a bit skewed and some flows or some application types might be missing. Dynamo might be able to add some of it to it to make the data set better. But obviously there might be completely different applications that we don't yet think about. So we would love to hear from you if you have something else in mind. So all of that sounds great, I think, but like, does it even work to begin with? So we actually looked at these 74,000 traces that we so far recorded while crawling through all the orchestration files that we found, and we saw 2 things. First of all, that all these traces contain diverse applications from from different types of applications. So we believe Dynamo will be able to answer various user specifications in a good way. And some of the traces, and therefore some of the applications, actually generated a large amount of traffic. So even though that we only at most recorded 10 minutes for each application, we had traces that had millions of packets, 100,000 of flows. So there's certainly the potential for traffic there in these open source projects. And we believe that that is a good start to dig deeper into this. And with that, I'm already nearly at the end, where today I showed you how Dynamo kind of bridges the gap from static text or code to the actual network data. Besides Dynamo's approach of rerunning the projects, there might be completely different approaches to do something similar. We could also look at metadata comparisons, perhaps inferring similarities between different open source projects, or perhaps machine learning-based approaches might allow us to learn the behavior of the applications. And in the distant future, perhaps you could even think about doing the reverse. Given some network traffic, what would be the code or the text that actually produces it? So today, there's a lot of research in general for programming languages, auto-completion and so on. So perhaps in the future, we could also think about similar techniques for networking functions. So give me kind of a function that now produces the TCP traffic I need for them. And finally, if you are interested in figuring out which projects we identified when we went through the entire GitHub repository, or even which of these actually generated some kind of traffic in our setup, please follow this QR link, which gives you a list with the data set. That's it. Thank you.
Hi, I'm Akshay from Berkeley. I think the characterization of this work, which is super cool, as a gold mine, seems like kind of apt to me, because like most mines are mostly giant piles of dirt. Like how much actual gold is in the gold mine, and how much is actually dirt?
Yeah, so I would say with the, let's say, very simple approach that we used so far, for example, we use the most default Docker Compose up command in order to run these repositories. We have quite a low success rate of getting the projects to run and then produce traffic. What we can use though is a huge amount of projects, so we can always find more in order to find more. But I think, for example, just we did a simple test, passing the README for a Docker Compose command, and then using this one instead of the default one, already has much higher success. So in the future, we try to iterate on this front as well, that we, to begin with, can identify many more projects that actually generate some traffic. And obviously, we can scale to other techniques, Vagrant, Kubernetes, or like other orchestration networks.
So in the end, do you imagine having to sort of, after a bunch of automated techniques, manually go through and find the traces that are actually gold, or do you imagine automated techniques being able to go all the way to the end?
I would hope that, I mean, eventually we are able to just perhaps once code the way to automate a certain automation framework and run it. And then we have to spend some time, but we hopefully just by default get some gold out. But then again, we are not replaying the traces. We would then replay the actual containers in the hope that then they do kind of the same thing. And that still also needs to be reevaluated. Okay.
Thank you, Tobias. So a few quick questions here, but later on, if you have detailed questions, just move it to the panel. But go ahead.
Yeah, so just a quick question. You're taking like a lot of online GitHub repositories, and you do not know whether the online GitHub repository, whether they are generating like an, what about the correctness of the traffic they are generating? Because we do not know, and there might be some issues in the actual code itself, or like they might be generating anything which is not representative of an actual phenomenon. So is there any step into the correctness of the traffic which you generate?
So at the moment, we just try to find traffic, and they could be wrong, or it could not follow RFCs or other things. And I think it might be a different or interesting research direction to automatically check for correctness to see how that is the case. But I think it could even be a feature in some cases, and in some use cases, that not all the traffic is perfect, as you would see it in a real trace that is collected from a link, because that might also be interesting for some testing, for example. So at the moment, there is no step, but there would certainly be a way if you can characterize what is correct in order to do a check.
Michael Wetzel, University of Oslo. I'm blown away by the craziness of this idea. It's really amazing. I mean, as many as others have said, this is gonna I mean, there will be strange traffic right from some of these applications. So at least, I mean, I wonder if you have this example of database traffic, like how do you detect how do you get this category? Like,
Yeah, so at the moment-
search word or what is it?
So at the moment, the categorization was mostly done based on the parts that we observed in the packets, which obviously is not the best characterization. But we also saw is that some of the characteristics of the traffic, for example, speaks for database, like there are very short request reply style of traffic. There's one packet going on, we get an answer, and then perhaps the flow is terminated again. So, but at the moment, we basically were more focusing on collecting data, and now we would need to dig deeper into it to really categorize or perhaps figure out what exactly the type of traffic.
Very well.
We take one more question and then the rest in the panel.
This is quite good approach to collect the data from GitHub, but I'm curious about when you see the repository in GitHub, there are so many variations in coding style, like using alias is something else. So how do you collect it? And one more thing is there are so many userless repository in there. So how do you cut this repository for when you collect it?
Yeah, so at the moment, what we did is GitHub has an API search query, and we kind of search for repositories that contain at least one Docker Compose star file. So it could be a different name, because Docker Compose is one of the orchestration frameworks that Docker uses. So we kind of already filtered out all the repositories that do not contain any of these files. So at least we knew if we clone the repository, there is at least one file that we believe we can run. That doesn't mean that it generates traffic or that it actually works. But obviously you could search for other things. As you said, there are different automation frameworks or implementations to test, and you could also do metadata analysis in order to figure out if the projects contain that or not.
Thank you. Thanks so much. Next speaker is Dr. Kevin Du. He's a professor at Syracuse University. He received his PhD from Purdue in 2001. He founded the Seed Labs open source project. The cybersecurity hands-on labs developed from this project are now being used by over 1,000 institutes worldwide. He self-published a textbook, Computer and Internet Security, a hands-on approach, which has been adopted by 247 institutes. He's a recipient of the 2013 ACM CCS Test of Time Award and 2021 ACSAC Test of Time Award as well. So Kevin.
Yeah. So I'm going to talk about the Seed emulator, and so this open source project has been open source for already 4 years. We've been spent already 4 years working on that. And so just a little bit of the motivation. So why do we do that? And initially, actually, this was come from for education. I came from cybersecurity community, and I developed the labs and so for cybersecurity education for the last 20 years. And so I got 1,000 universities worldwide using that. But one of the things I do not have is I teach BGP attacks, and I have no idea how I can get my students to work on the BGP attacks. So every semester, I have to apologize to my students because that was the only one in my class without hands-on exercise. So until I find somebody who could build this internet emulator for me. And so that is what I'm going to present. So as I said, the initial was for education, but once we open source it, I actually received the request from the research community. And they said, oh, I could see this in my research lab. So I said, oh, that's great. That's really beyond what I actually designed this for. So I actually talked to a lot of them. And then I decide, okay, I'm going to submit to the HotNet to see whether they actually really like this or not. So I actually submit that, and I'm glad this paper got accepted. So at least there's positive things. I actually, before that, I did talk to a lot of the network expert. I was asking them, okay, do you think this is useful? And they will ask me a question. They said, give you 5 minutes, convince me, and why this is good than some other things I've been using. So I did not have a good answer until I started writing this paper. I said, okay, I got to think about this. Now I summarized into here. So what is good for internet emulator? Now first, you got to be a good network emulator. And so this community already know a lot of this. But internet is not just the network emulation. And you also need to emulate in the internet infrastructure, that including the autonomous system, internet exchange, BGP, peering, and all of these are not easy. Okay, so if you want to build that into the emulation, and that is not easy job. And the reason why I got that student, because he spent $6,000 per year and to own a real BGP router. That's why he had real world experience. And he spent $6,000 just for fun, not for any business. And that's the reason why I have a student in my class who know how to build this. So, and this is not enough. If you want to have a good internet emulator, you need to have a good service. You need to provide support for the service. For example, for the DNS, right? These days we have a blockchain, right? Can you run blockchain on top of your internet emulator within this computer? I can run Ethereum network 50 nodes inside this computer without any problems, right? And only took me 15 lines of Python code to be able to generate the internet emulator to do that. So that actually will really shine, okay? So the most important decision that we made actually when we designed this, and there are two actually most important things. One is we decide to separate emulation, conducting emulation, and build emulation. A lot of this work, they have to integrate them together. That is complicated. Running emulation is very complicated. And we actually, like the previous work, and we used the container, Docker. Docker did a fantastic job to do that. So that actually make our life easier. So we just need to build that. And to build that, that was another decision we have to make, because a lot of our existing work, they have a different way to build it. Eventually we decide, we're just going to let the user write a Python code to build that. And that will be much easier. So that basically what we are doing is we have to build Python library. For every single element, essential element of internet, we're just going to build a Python library. Now the user will just use the library and then to build their own internet, whatever they want, whatever topology they want. And then we have to write a compiler for the Docker, and we just compile everything into the Docker file. And then you hand it over to the Docker and let the Docker run using the Docker compose file from the previous talk. So that has become very easy. Our emulator does not depend on container. If tomorrow some other technology becomes more popular, we just write a different compiler for that. That just probably takes a few weeks of work and to do that. So the work on top is really not depend on any underlying technology. Just give you an example. And this example shows you how to just construct in the transit autonomous system, right? And you have a code here to generate a create network. And then you have an API to create the routers. The topology is really how you use a router to connect with the network. And you see some of the router, they got to connect to the internet exchange. The one with IX 100, YX 101, those are the BGP router. So because internet exchange, if your router connect to internet exchange, that is a BGP router. And we will configure that router particularly using the BGP. And the router itself is not enough, you have to peer. And we actually implement the peering. So you can see these 2 lines of code, and we peer several autonomous systems together. And underlying this, there are a lot of Python code, because BGP peering implementation is very complicated. You need to know the practical side of BGP. For example, the relationship, peering relationship, right? When I peer with you, what is our relationship? Am I the provider, customer, or are we the equal peers, or are we some other business relationship? All of that have to be captured. And so we have to implement some of them, not all of them, but we can implement all the complicated business situation. And some researchers told me, they said they want to customize their node. Then we said, okay, we just implement some low-level API, so you can customize individual node, install software, configuration, everything you want. We also have a visualization. So we have to visualize, and this way I want to show, not just I just want to show you, I'm running this internet emulator right inside my computer. And these are 70 nodes. And the resource consumption is not really a lot. So it's 70 computers inside here with 5 internet exchange. The star are the internet exchange. and those are the network, and this one are the BGP route. Okay, so they can visualize, and so if I want to do this, I can just do, you can click on this, you're gonna get terminal for that node, and you can just pin. And the pin will work, and I actually enable the actual filter, and so you can see the traffic. If the traffic is too fast for you to see that, and you can do the record and replay. So I'm gonna record and stop and replay, and you can see the traffic and one by one. So we actually did a lot of things all based on the need from the research. And so we listened to the research community a lot, and just to figure out what should we provided. So those are the things. The best thing of this is this service component. When we design the service, we want the service to be like a chip. We don't want to hard code the service into the underlying internet. So they can be pluggable to any underlying. So I can build an internet emulator like this, and then build a component like this, and I can plug that into, just like chips. So we have to build a lot of this already. And you can tell I'm from the cybersecurity community. We built already the Tor and the .NET and the botnet. We have to build a blockchain. That's my current work, and we are trying to support the most recent the Ethereum, because they migrate to the proof of stake. That actually is not easy to actually to support, and we're actually working on that, and we do have prototyping. So a lot of things actually are building into here. This is just a few lines of code. How I create Ethereum blockchain, you can see, you can fit in one slice. And if you want more, you write a loop, right? That's the benefit of writing the program to do that. And we can create money, right? So here underlying this, I can create as much rich account as you want because you own everything. That is the beauty of that. And you can, and here's some I run, you can see I run 50 nodes on my computer. And not this one that I'm actually displaying, but you can see that I run everything in my VM, not on my physical machine, on the VM. I give 8 GB, and you can see that they run very well. We also want people to connect to the real world from the emulator. So we actually implement a very simple thing based on the BGP. And so you can actually reach out to the real world from the emulator. Okay, so that is we call the shadow internet. If your computer, one computer is not enough to emulate your size, that's fine. You bring a few more computers, you buy a little bit of things called the switch, you bridge them, and now suddenly, and you have all these emulator, they bridge, they form a larger one. And all of them are dependent on BGP. I'm not using any artificial things. It's just if you configure your hardware and the BGP correctly, and you would have everything. This is one fun thing I did. I bring this to my class, and I let students to connect to my Wi-Fi, which is connect to my internet emulator. I let them to connect their smartphone. I said, now you connect to the internet through my internet emulator. And now I'm going to launch the attack against my university. And I'm going to hijack the BGP prefix of my university. As soon as I do that, and everybody lose the connection to the website, to the university website, and they can steal and browse Google and other places because of BGP attack. So that was actually striking for the student, because I can do that live in the class. I just need to actually connect one access point and to my internet emulator. And some of Google using IoT, they actually connect IoT devices to the emulator, and then they conduct research on the IoT. And this actually was used by one of the research groups. I actually did this lab, and so I asked students to write a worm, okay, internet worm, and so they will release the worm from one of node, and this is all inside my internet, and they were gonna write the simplified voice worm, and they're gonna release that, and then they're gonna see how the worm crawl from one computer to another one, eventually conquer the entire internet. Okay, and this is one of the project I called yesterday once more. I want to recreate all the famous or notorious the internet incident, and that you bring that into the education, so for people to learn from the past. So that's basically the end, and I'm really interested in learning the feedback. And so what is this useful to your research or to your classes right? And what are other features you would like? And all the information I already put in here, and you can actually get the code, everything. If you do want to save some time and you say, I want to get my student to start this or run this, I can help. We can do a Zoom, and I can help you get this started and within 30 minutes, and then you can play with that, okay? Thank you.
Just two questions.
Okay, amazing talk.
Thank you.
My name is Selek from Princeton. So you mentioned running Ethereum or like even Ethereum with proof of work, not proof of stake, that is currently. So can you elaborate on that? Like, are you using their actual code?
Yes.
Or
Exactly, receiving the code and with the POS, which is a use they run the beacon, the network, two network, Ethereum network and beacon. And both of them are using exactly the same source code.
Gotcha. And so my question is more on like, so Ethereum will start creating transactions, they'll like, so the actual traffic that you would have to deal with depends on what the nodes are doing.
Yes.
How do you kind of trigger them to behave as proper Ethereum
Yeah,
nodes?
very good question, very good question. Yeah, right now, and I've been just generating a random transaction. I have a script which generates a random transaction from random account, and that will generate the traffic. In the future, what I really want is to bring some real world transaction, somehow map that into my emulator. So I can not directly use real world data, but somehow mapping that and then fit into my emulator. That's something I'm thinking about.
Thanks.
So I'm Henry Birchley from Princeton University. I do a bunch of work on BGP, and I think one thing I've noticed a lot about real world BGP is that things happen at the rough edges. There was an incident where an experiment crashed FRR routers because of a new BGP extension. And so it seemed like a lot of the BGP commands were very high level, like I want to peer, I want to do this. I was wondering, I guess, sort of what software stack of BGP are you running? And I presume that the software stack for the BGP and how it's exactly configured is something that you can change in that.
Yeah, we are just using open source the code for the BIRD, BIRD.
For the BIRD.
Yeah, that's been widely used. We could not write the BGPs, the code ourselves, but we just install the BIRD and we configure. The student that I mentioned, he was very experienced in the operating the real BGP. That's why he know how to configure that. I didn't know.
So the emulator is an interface for making BIRD configs that properly interact in a sort of internet manner. I presume that it could be extended. Have you considered like a Quagga interface? So I could have half of my internet routers running Quagga, half running BIRD, or it's just.
It could be, definitely. Yeah, right now it's just building, we just use a BIRD, but definitely if there are other software and we could have another version. And so I was even talking to the agent and we're thinking about maybe put this Scion in the emulator, right? That could also run. So a lot of things, I mean, it just, the framework is there, right? And the actual code to including some, and we just need to write additional code.
Makes sense, thank you.
Thank you. Let's thank Kevin again.
Thank you.
Next speaker is Silvery. He's a PhD candidate at Berkeley, where he works on systems in the NetSys lab and is advised by Professor Sylvia Ratnasamy.
Before we start, I may be coughing during the talk. I'm tested COVID is negative. I need this season. So those of you in the front row, don't get intimidated. All right. So in the previous two talks, we heard about this sort of simulating and testing networks with these amazing techniques. Now let's go up a level and sort of switch gears to the network applications, and specifically prototyping for IoT with Digibox. So IoT devices are becoming increasingly pervasive in our living and working spaces. And this opens up possibilities of new applications that can help us make informed decisions in our daily work and life. So for example, the building manager of a commercial building may use smart building apps that consume data from occupancy sensor to monitor building occupancy alert about overcrowding during pandemic, and optimize for space utilization. So how is this done? In IoT deployment today, there are physical devices like sensors and actuators. They can be accessed by the application via the device driver, and the developers, they can specify application logic that make use of the devices. While in both academia and industry, many have studied and proposed IoT frameworks for the applications. Dealing with the physical infrastructure, however, remains challenging for application prototyping. This is because buying and setting up these devices can be time-consuming and cost-prohibitive. And thereby, it can be agility bottleneck during prototyping, for example, for research, demoing a product, or teaching them in a CS class. So our community has tackled such challenges in the past, and Mininet, in particular, is a prototyping environment for SDN, which allows developers and researchers to create, to test and play around with the virtual network. And making it like a first story for researchers and students to prototype and to learn about SDN and networking in general. So, but what about the prototyping environments for IoT apps? Let's take a high-level view. One can prototype with real-world test beds, data as I mentioned. This is most realistic, having high fidelity, but it can also be difficult to set up. On the other hand, today's prototyping solution with device simulators are more easily accessible, where they focus on simulating the device hardware capability and generating the device data in isolation. However, such simulators, they fall short in capturing real-world events, such as human inputs and interactions between devices. For example, correlating the detection of motion across occupant sensors in the same room, or when simulating a user turn off a fireplace, then the temperature sensor in that room should sort of reflect it. What we want is to be able to improve the fidelity of device simulators by allowing the developers to program for human interaction and correlated behaviors, but still be able to easily reproduce and reuse the testbed in a scalable manner. And Digibox is our proposal towards this goal. Our key insight here is that the IoT prototyping environment should go from device-centric to scene-centric, where the developers, they can simulate not only the individual device behaviors, but also the correlated behaviors in scenes, such as rooms and buildings, etc. So how is this done? Let's take a look at the design of Digibox with the help of a few simple demos. So first of all, Digibox provides 3 key abstractions as building blocks for the scene-centric prototyping. So the mark emulates a device in the IoT app, while a scene represents an abstractions like a building or a room. And we attach marks to scenes. And when we program or simulate a scene, this is reflected in all the marks attached to that scene. Together, these abstractions support the design priorities that we will go over next. So let's first check out interactivity. So in this quick demo, we'll start a mock-up device, a mock lamp, and which will be pulled from a remote repo. And the CUI we'll use is called Digi. We will pull, run, and turn on the power of the mock lamp. So now let's take a look at the demo. So we'll first pull the Digi from remote repository. And we'll run it. We'll then check its status. As can be seen, the lamp is currently powered off and has a brightness level of 20%. What we're going to do is we're going to turn it on and change its brightness to 80%. And then we'll check its status again. As can be seen, it's currently turned on. So with this approach, we can use Digibox to spin up many sort of lamps like this. And then we can, for each of these lamps, we can query for its sort of log of changes, or even do some simple analytics on top of it. So now let's look how this is done underneath. So each mark has 2 components, the model and the simulator. The model is a declarative interface with key value pairs describing the mark desired and the current states. The simulator watch for the model's changes, run its simulation logic, and updates the model. And the simulator can also generate events, as we will see in a later example. Finally, each mark will run in their own microservice that can be added to the simulation independently from others. So in the next demo, we will see how to use Digibox to create a scene for a room, and then the room to coordinate the ensemble behaviors of two mark occupancy sensors. We will be using the attach command to do so. Right. So like before, we're going to pull this pull these marks and scenes from remote. We're going to run the occupancy sensor for the desk, then for the ceiling, and then we're going to check. So look, here there are these two sensors. They are isolated, so they will have sort of unsynchronized behaviors. Now what we're going to do is we're going to create a room scene, and we're going to attach these two occupancy sensors to this scene. And as can be seen, now these marks will have synchronized behaviors and they follow the sort of human presence generated by the room. So why this is happening? So first of all, Digibox allows simulating the scene just as the marks, where each scene has a model and a simulator that can generate events and run simulation logic. Then the marks can be attached to the scene, by which the scene can update their models and coordinate their behaviors. In fact, in Digibox, a scene can be further attached to another scene and so forth. For instance, given two rooms and the marks in it, a developer can create a building scene that has two rooms attached to it. They can set, as a simple example, the number of humans in this building to be 1, and the building simulator can then randomly decide which room this human should be. And that room, say office, will have the human present. And the room sets its occupancy sensor to detect it. But the other room has no human and no motion. Further, in Digibox, developers can specify conditions on the scene that need to be met. For example, let's say the RT applications turns the lamp in the lounge where there's no human in it. Such a violation will be logged by the lounge scene and used for debugging later. Now, in this last short demo, I will demonstrate how one can use Digibox to take a snapshot of the marks and the scenes. And to do so, we will use the commit command and the push command. So we will first commit the lamp we used before, L1, making a snapshot called the working lamp. And we will create the new lamp, L2, based on the snapshot. As can be seen, the L2 has the identical steps. And now we'll do the same for the office scene. Note that for the scene, because it has the marks attached to it, so the Digibox will commit the scene and marks along the hierarchy recursively. And we'll now create a new, we're going to create a new office scene, and it should behave the same as we've seen before, the original one. So due to time limit, please refer to our paper for more information and about the functionality of Digibox, including how to develop new marks and scenes and integrate them with the apps, and Digibox microservice-based implementation, and how to effectively manage, share, and reproduce the marks and scenes. So now, putting these pieces together, we propose an end-to-end prototyping workflow with Digibox for IoT applications. So developer may choose an application framework and runs Digibox as a prototyping environment. She can write the app in the application framework while writing scenes in the Digibox. And during testing, she may run the scenes and run the apps to interact with the logs. She may use the logs, for example, to debug and to iterate the process and to improve the application. In the meantime, other developers, they may use their Digibox to also download and reuse these scenes, run the scenes to test their application, or use the log to reproduce each other's experiment results. So in conclusion, our goal is to accelerate IoT application prototyping to allow interactive and reproducible simulations, capturing both individual and ensemble behaviors. And to achieve this, we propose Digibox with these 3 abstractions to support scene-centric simulation. and as well as an end-to-end application workflow that uses this. With that, oh, I have some slides, but it's possible. With that, I'm going to take questions. Thank you.
Any questions?
Hi, so I guess I'm wondering, do you have a physical simulation? So what happens in a room with a light sensor and a light? When the light turns on, does your light sensor correctly detect? And if not, how, like, isn't that where some of these ensemble behaviors really become hard?
Right, so I see there are two parts of this question. One is where the physical simulation happens. So we envision that happens on the mock digits, where you can say, take a device from a vendor and you're going to simulate its behavior. But sort of how to coordinate across device, that logic exists in the scene. And there are cases we envision in the future. For example, you have some robotics that can be harder. But for the starting place, we're dealing with these sort of smart space applications where that's sort of current design is enough.
Wait, so the developer writing the scene is the one who has to connect the light to the light sensor in my case?
Oh, no, it's the developer who developed the mods that we're dealing with this sort of device takes on.
Thank you for the good call. I'm Hopper from UCLA. I'm interested if you planning to design a visual interface, for example, it's on Unity, so you can visualize with that what you have in the as a backend and visualize this in the front end with like game engines such as Unity. This is my first question. The second question is a lot of IoT devices today they communicate with wirelessly. So can you engine like kind of simulate those? Because Wi-Fi is lossless link. Can you simulate like those interactions? Yes.
Right. So both are great questions. So the first one is about how we sort of use like game engine, physics engine to sort of simulate these physical effects. So that's actually one of our ongoing sort of exploration, how to integrate these parts with those simulations. And the second part about connectivity, I would say similar answers. One can use, for example, TC to emulate these connectivity issues that you can put in as part of the framework.
Thank you. Could I have all the speakers up here for the panel?
Sorry. Hi, I am Venkat Arun from IT. It's a very interesting lineup of papers in this session. Thank you for it. So a lot of people are developing simulators for a lot of things. How feasible do you think it is to sort of combine like this component from this simulator, that component from this simulator to build one unified thing? There are also papers, this SIGCOMM. And how feasible do you think that vision is? Are there differences in the philosophies of various simulators that would make this infeasible, or do you think that's possible?
I can take a first crack on it. Yeah, so because when we developed this, that was the first thing we're trying to do. And we're trying to say whether I can leverage existing work. And so we spent 2 years actually trying those things. One thing we tried is we're trying to use NF3 as our engine, underlying engine, and we build AlphaSoft on top of that and trying to get that to work. It works, but it's nightmare. Yeah, because just to get Hello World to work on the NF3 is not easy. Now think about the Ethereum software. So that we tried several things, and then eventually decide we're just going to actually use existing Docker, which is actually the network simulation, emulation, the platform, right? Become very, very mature, and that's where you actually decide to go that route. Yeah.
Perhaps I can say here something, not for the work I present today, but I'm also an author of this media network design as well, which is doing a bit similar things with Docker containers and so on. So I certainly think that there might be possibilities to connect things together. Perhaps more from a personal story, I actually, for my own work, tried to do some research on it and then make a publication out of it. And some of the reviewers' comments were that, oh, that's great, the emulations and so on. But actually, I don't believe that, for example, the delay used for into AES links is actually what you would see in the real world. And obviously, there are a lot of pieces that perhaps are still missing if you really want to say now it behaves as the real internet, if that is the goal. It's not necessarily for teaching, for example, the goal. So I mean, we would perhaps also need some work on combining results from measurement conferences with the actual simulators in order to make even a stronger platform in the end.
Let me add one more insight to that. Yeah, so we actually, when we look at existing the tools, a lot of them, they actually built at the Docker. They actually, but now if you look at how they implemented it, a lot of it, some of the tool, and they actually using the Linux namespace, which is the underlying technology, underlying the Docker, right? But they are trying to do what Docker is doing, right? So you will see, I see a lot of them, and some of them the work, and they are even trying to migrate into the container base. So I think in a sense, we are kind of converged. And so you can see a lot of our work, actually, we are using Docker and maybe some of the existing tool, and they will probably converge to that. And Docker does have some disadvantage, which means it's very hard for you to really fine tune some of the network unless you dive deep into how their virtualization is implemented. Right, that's a lot of existing work, and the three, I mean, those are their advantage, right? So eventually, I mean, it's really the convenience of use and versus the actual capability to fine tune those networking. Yeah.
Right, so really cool to see all this work on research methods. This is at least a question for the first paper inspired by the third paper, but maybe a question for everyone. So when you're grabbing these many tens of thousands of repos and running software, it seems like how that software runs and the traffic that it generates depends a lot. In the real world, it would depend a lot on the environment, the context, the users, and the user side workload, client side workload, or even specific objects that are populated in databases. Maybe I missed it, but how much of that do you capture already? What have you thought about starting to capture? Are there other ways in which the emulation methods discussed in this session, need to capture more of the context?
Yeah, so perhaps for the work I presented, like at the moment we are kind of just trying to run them and hope for the best that we get kind of some interesting traffic out. But as you correctly mentioned, like if it's a database application, if you don't make good queries, the traffic you would see might be very limited or not there at all. So, but we believe the next step would now be that we have some sort of initial data set with the traces we already collected, that perhaps we can start to infer a bit. What is the behavior, or how could we connect even one container to another in order to increase the traffic? But that all needs to be done in order, like that's not yet there. But at the moment, we kind of run it and hope for the best, but that can be limiting the entire traffic we get.
Sydney, would love your thoughts on this as well for the IoT devices. I guess the same points would hold. So what would be your take on that?
Can you repeat the question again, Brighton, in this IoT context?
Yeah, I guess the high level question, which could apply to all of these scenarios, is how do you capture the context in which the system is running? And I know to some extent you've thought about that already and developed methods. Is there more that you want to capture there that would matter for real world use?
Or even future applications, like how do you make it future-proof system that you're designing for some new, like one of the things that I've been working on is agriculture. How do I use your system for monitoring a farm? So that.
Right, so actually my take on this is that this kind of network application will interact with the physical world. And in the physical world, the demands is really heterogeneous and will be increasingly so. Rather than saying we build some solution that are future-proof because we run for generation of apps, we should enable them to sort of speed up the agility and make sort of the, I wouldn't say citizen sort of programmer, enable techniques sort of along the simplify creating new apps. So no silver bullet. Thank you.
Alec Alessian, UC Berkeley. My question is specifically for the last two papers or last two projects. So in real world, networks are really heterogeneous in that there isn't really someone controlling all the devices. We just have our heterogeneous systems and we come together and we make sense of our conversation with these protocols that we come up with. At least when I was taught networking, everything, I was playing God there, I was controlling every device. So would Seed emulator, for example, allow me to have multiple people connect their networks together and somehow learn this heterogeneity aspect of networking as well? And same, I guess, also for Silvery, where I have multiple devices, could I somehow connect multiple people developing these together and then having them interact among each other and developing together as well, like in the real world?
That's actually a very good question, and we support that. So if I turn on my emulator, I expose a port to you, and you can VPN into my network, and you could be physically, virtually attached to one of the network, and you will be participating in that emulation. So many users can do that. If I run it on the cloud and you expose the port. Right now we cannot because there's a lot of security measure for that. But once you get the VPN and you can actually get into that without any problem. It is a feature supported by our emulator.
So we have been working on a similar feature like that, where you have these different digibars, then you allow one digi to sort of send data to the other across these different test beds. And so I guess the setup will be similar, where you allow other researchers to log on to your sort of demands and things to
Matthew from Stanford. My question is also inspired by the second speaker, but I'd love to hear the whole panel's opinions. I think, so like in terms of teaching this sort of stuff, right? If I want to teach somebody how the internet works, which I would not be qualified to teach that, right? But it seems to me there's sort of two options here. One is you can kind of, emulate or simplify the environment and then run the real code, which seems to be what you're doing. Or you can sort of, have like a real environment, but then simplify the code. So like, write your own sort of have the students write their own sort of mini BGP and everything, and then have like a network of Raspberry Pis or whatnot. So I'm curious about two questions. One is, how do you think about the difference between those in your own teaching? And two is like, out of curiosity, how small do you think you could get like a minimum viable BGP-ish thing running? Are we talking like hundreds of lines of codes, millions? Where are we at?
That's actually a good question. I like both approach. And the main reason why my student, the second author, and he was very good at BGP, he basically wrote his own BGP software. He just wanted to learn BGP that way. So that was very, very valuable. I don't know myself how small they can get, but that is definitely a very good educational approach. Okay.
All right. Unless you had a comment.
Thank you.
All right, thanks very much.
Why don't you ask the questions then, Anoop?
Yeah, hi, I'm Xijun from Stanford. I have two questions. So the first one is, my understanding is that all the systems, I like them very much. It seems that they require some domain-specific knowledge or language for them to work. So for example, for network traffic generation, it seems like we're filling the blanks for like the particular requirements, just like specified in the first talk. So I understand a very intuitive question is, would it be necessary and helpful if we generalize the input format to natural languages so that it could benefit a wider range of users? And if it's necessary, what would be the major challenge in this case? Yeah.
I mean, yes, it's a good observation. Like we just kind of created our own specification language, and now you would need to dig into it if you want to use it. So I certainly see that there might be potential in kind of formalizing some concepts. What I think could be a challenge is then to make it fit to all the use cases. Like, okay, perhaps we try to think about everything. We have to define the traffic rate or the amount of flows, but then you would like to test something where that doesn't matter, but I don't know, you want to specify the inter-arrival packet time. So I just think it might be challenging to come up with a natural language that is broad enough to capture all the use cases you would have, but still kind of easy to understand and to write.
I do have a very interesting story behind this. Yeah, because it took us quite a while to actually settle on the path we are taking. Initially, we were looking at some of this work, and some of them use a graphic user interface to build the network. Some use what we call configuration approach. They write a JSON file, right? They describe how your internet should look like, right? And so initially, we decided graphic user interface is not scalable, and we decided to use configuration. And then my student and I had a disagreement how what language we should use. I'm more interested in a more concise language. He was more into something called JSON, which is more verbose, but actually more powerful. And so we decided, okay, so we cannot convince each other, so we decided to compete. We said, let's program this, and you program your version, I program my version, and to see who can finish first. And of course, he was a much better programmer, but he was like a deer. I was like, he was like Robbie, I was like Turtle. I worked very hard. He was sleeping half of the time. Eventually, I won, but the wins is not important because of that competition. We realized we were just looking for a language. When I programmed that, I wish I had a loop. I wish I had a variable. Because think about it, you have this large configuration file. You want to change something later on, and you're gonna say, oh, okay, I'm gonna change 100 places. That's when we will realize we are looking at a program language, and that's why we settled on the Python. And from there, and the design was pretty much done, and took us 7 months to finish the implementation.
Yeah, thanks. Another quick question.
Actually, we have to stop here because we are running late. We're 15 minutes late. And Aditya says we'll have to vacate the room at 5. We'll take 15 minutes extra, but on natural languages, we've seen, like you saw the GPT-3, it did quite well with hot text titles, and people are working on, even at Microsoft, when we have been building these Power BI applications, we are turning natural languages to SQL queries. Who knows in the future how you could transform them to these programming languages for network emulation. But great work and great talks, a great panel. Thank you. Let's thank the speakers again, and let's take a